Hi, everyone. I think we can start right now. Let me first introduce myself a little bit. My name is Lu, and I'm assistant professor working at Institution of Marine and Atmosphere Research Utrecht at Utrecht University. And my background is all about the ice part, that is Cryosphere part, and all about the remote sensing. But I do a little bit atmosphere science during my bachelor program. You can call me. Yes. Not for you. So I still see just a little bit participants in these sessions. So I'm not sure what the background and why you're interested in these Cryosphere sessions. But this tutorial, I prepared a lot about this notebook, but we will not go through everything. So we're just maybe half of them, but you are free to download the notebook and download data by yourself and then do a little bit try because all the codes already. So first of all, if you haven't downloaded your notebook or the data set, I would strongly, where is my PowerPoint? Recommend you to download from GitHub and download the data from the Zhou. And for your record, the data is a little bit large, maybe 6 gigabytes, I think, in total. But every notebook have their own data, so some data are quite small. So you can start with the SAR data you're downloading. Did you have access to this tutorial already, or download the notebook already? Is it on the downstairs?
It's in Mattermost. If you like search JavaScript on Cryosphere, you find it.
So I'll give you some time to find this notebook and to download the data because some of the data are quite large, but I'm not sure if you can download it well. So just for your reference or for your background about the Cryosphere, so can I switch the slide right now? Okay. So just the previous will be like some about 20 minutes, the introduction part. So you're free to use the time to download data and the notebook. So first of all, I am not sure your background again. So I wanted to addressing about the importance of the Cryosphere or the polar regions. And in terms of why we care about the polar or the Cryosphere one. So the Cryosphere is, as I said before, is all about the ice part, the ice in the glacier, the ice in the land, or the Antarctic, or the Greenland part, or the Arctic part. So I want you to give a approximate guess. What if you melt all the glaciers on the mountains? How much of the sea level rise can, or just give me a quite approximate, about meter or 10 meter, 1 meter? A little bit less, only about 0.3 meter for all the glaciers, including the Alps and Himalayas. So another glacier part, we're going, not glacier, but ice sheet part we're going to addressing is about the Greenland. If we completely melt the Greenland ice sheet, how much of the sea level can be rise up? Wow, you are very bold into give this assumption about 10 meters. No, 7 meters. And then the largest part, which is still a mystery for us, is about Antarctic Greenland. So that is about 7 meters. So for the Antarctic, how much it can be contribute to the total and global sea level rise? How? 60. Yes, quite large, right? So this is from the glacier, Greenland, and different part of the Antarctic ice sheet part. So as we can see, previously, it will be the huge risk, especially in Netherlands. So the thing is, do you know IPCC? How many of you know IPCC or all of you? Yes, great. So according to the sea level rise contribution from IPCC, what you can see is, first of all, it's not just about give you the simulation during the past or the historical run, but also give you the scenario about the future, the CO2. So as you can see, this is a contribution for the future scenario in terms of different CO2 emissions. So the glacier, Antarctic, and Greenland part. And the red part, as you can see, one at least at the end of the next 2 centuries, we see a large differences or large in terms of the sea level rise contribution. So the sea level rise contribution is not just based on this the ice melting, but also partially is based on some what we call the ocean thermal expansion. Because when you have the higher temperature, the seawater will going to a little bit higher, or the volume will be higher because of this the thermal kind of expansion one. But still, we still have the uncertainty comes from this 4 different the sources one. So I'm going to walk you through a little bit about the background about first of all, the Greenland ice sheet melt. So this is the melting date, which we are going to walk through this exercise today. And this is the melting date in 2021, and this is a general one. For sure, I bet you have nothing about or have no idea about what it means. But if you take anomaly comparison with the climatology anomaly part, which is how much of days is melting within the Greenland, and you can see all the, first of all, it's all in red. That represents it's not again, or no, not again, but significantly. But also, the melting is extremely long. Is the age, which is a low elevation of the Greenland part, and so much of that, like how much of the area is being melting in 2021 compared to this climatology one. So still a lot. And one thing that is one of your exercise part, and next exercise part is about the ice sheet mass balance in the Antarctic. So this animation is completely from the GRACE, gravitational, gravitational, the satellite. So as you can see, with the observation since 2002, we can see both Greenland and Antarctic are in huge mass loss, especially Greenland. So still loss everywhere. But Antarctic, the ice balance is kind of in less distribution. So most of melting is located or within this, what we call doomsday glaciers, the wasted glaciers. But this part is still kind of okay in terms of compared to the climatology one. So, and this is what we have now in 2023. Still quite a huge loss in terms of difference, the Cryosphere regions. And I'm not sure if you have some idea about how large the Greenland or the Antarctic is. So I'll give you one short about the Larsen Sea, the B. This is the Antarctic Peninsula. So Larsen Sea is here, and you can see this is just several snapshots occurred within, I think, 1 month, about how huge the ice sheet, or what we call ice shelf, is collapsing from the ice sheet, part. And this is before the collapsing and after the collapsing. It's within 1.5 months. Yes, a huge of ice is lost. And that part of ice is directly contribute to the sea level rise because it's completely freshwater input for the global ocean. And another part, because this is occurred, I think, in 2002, and another melting is occurred in 2022. So again, just within a week, a lot of what so sea ice is my topic anyway. So a lot of the sea ice is breaking completely, like detached from the peninsula or the ice shelf or ice sheet regions, and this is what we call landfast ice. So this part of landfast ice is quite important to keep the stability of this ice sheet or ice shelf because of the carving. Because once the landfast ice is missing, it's highly possible that this part of the ice sheet or ice shelf is easily can be moving around. And we will go through how to detect the velocity of the ice sheet from the SAR images later on. And I just got the news about the largest iceberg in the Antarctic is breakup. So this the iceberg is called A23A. And this iceberg is, first of all, detaching from this Phoenicia ice shelf since 40 years ago. And it's going through, stay here until 2022 is stuck within the Antarctic Peninsula regions and recently going to the South Georgia. And South Georgia, I think this is the domain of the United Kingdom. And the one way that we can detect this or track this iceberg, that is because this is from the Sentinel-3 images, but we can also track it or detect it from the MODIS satellite. So I got the recent news that this iceberg is going to continue to drifting away, going to the north part. That means it will maybe contribute the largest freshwater flux from the Antarctic or the Antarctic ice sheet part. So here is what is. Can I play the video here? Because it's the news from the sky.
It's just one of those.
Significantly, have a lot of freshwater fluxes for the ocean one. So, and just a little bit like wrap up a summary about the difference between the Greenland and the Antarctic one. So, yes, so the Greenland right now have a significant mass loss, about 0.7 millimeters per year, but the Antarctic is kind of okayish, and most of the Greenland, the surface melt is about the surface one, while the Antarctic is more about ice is breaking down or carving from or detaching from the continent, which is only the small part if occurred over the surface one. And again, for the sea level rise or for the directly surface melts can directly lead to the mass loss, while, as I said before, the Antarctic is more about how the ice is detached from the continent, while the surface melt is kind of indirect, the contribution. So we are going to have the exercise about how to detect the surface melt from the ASCAT scattorometer satellite. Have you ever working on scattorometer before or heard of before? Some not. But it's fine because what we are using the scattorometer is just kind of set some threshold, because for the surface melt, the scattorometer can let us to know how much of the signal comes back to the satellite or the sensors in terms of the C-band. So this is about the ice of the land. What my interesting or what most excites me is about the ice of the ocean, that is the sea ice part. So Yes, sorry. So the sea ice part is, first of all, I bet most of you heard about how the sea ice is changing both in the polar regions. So the Arctic sea ice, of course, is decreasing all the time for the past 45 years, and extremely lost around the marginal the sea regions such as this Siberian Sea, the Barents Sea part, which is huge loss in terms of the data in 2024 and go back to the 1979. And that is the Antarctic, the Arctic one. So the Antarctic also has the sea ice part. For the Antarctic sea ice, which is a little bit tricky because before 2017, everyone thought the Antarctic sea ice is increasing a little bit. But since afterwards, it's going down until 2025. So everyone is looking at what happens to the Antarctic sea ice, and just give you an overview about how much of the ice is lost in terms of the climatology with the 2023, the extreme loss one. This is the red part is an anomaly, which is being in a sea ice loss. So as you can see, the sea ice is losing like everywhere, and the part, or if we make a sum of this red part, that total area is completely larger than the whole the UK, including the applications sea regions. So as we can see, the cryosphere right now is have the astonishing changes over time in terms of the ice of land and ice of the sea. So how, I mean, this morning I just got the question about why do you think that satellite is the best technique to monitor the cryosphere? That is because, first of all, the cryosphere is not quite easy to reach out. So the something can get up the different skill, like the techniques to scan overall. So I'm going to walk through with you about the overall the techniques in terms of the snow and ice or the overall cryosphere region. And this is quite busy figure. And this spot, all the satellites can have the capacity to monitor the cryosphere changes. So the bottom panel of the bottom layer, the bottom is about optical in terms of Landsat. The Chinese satellite HY and FY, Landsat 5 to Landsat 8 and 9. And here we have passive microwave one, including the SMOS, SSMI. What else? The MSRE and TAO2. And up a little bit about the gravity, including the grease and the grease flood. And a little bit up about the elevation changes can be detected by the altimeter, including the CARSAT2, ISAT2, and the future crystal one. Scorometer, we have a SCAT, HSCAT, or SCAT. And a little bit up about the SAR. You've heard Echo, and he had amazing introduction this morning about the Sentinel-1, but not just about Sentinel-1, but also about the ALOS-1 and ALOS-2, and what else? Radar set, but the quite old one, and RCM, which is a Canadian satellite, and in the L band, because different bands for the SAR have a different the utility or the advantages to complement with each other. And from this different satellite, as you can see, a lot of like the what we call essential climate variables can be detected from the different signals. So in terms of my favorite sea ice regions, sea ice extent or concentration can either be detected from the optical, passive microwave, gyrometer. So not just one sensor can derive one parameters, but some parameters can or individually derived from different sensors. And in terms of the land ice or ice sheet elevations, it can be detected from the SAR, especially SAR is quite unique to detect the ice sheet velocity or how fast it can moving. And sorry, I should keep here, right? So this is just an overall overview about what the satellite, what the kind of a satellite, what type of the sensors can be detecting in the cryosphere. So I won't here. And I think we can start with our first, just a little bit test about the SAR examples of the ice sheet part. And if you open your notebook SAR, about SAR and download the SAR data, which is about 100 megabytes for you to download. So I will give you a personal example, just overall about what we're going to do for this exercise part. So again, we are going to use example 1, the 2 images to detect how much or how fast this this part of ice shelf is going to breaking down, or the carving or whatever the movement part. So one of the quite unique technique is called interferometry, the SAR, which in terms of interferometry is not quite technique, but it's quite unique for using the different SAR images to detect the phase changes. Because when you're passing by from the T1 to T2, you have the 2 different acquisitions of the images. And when you do this interferometry together, and you can get amazing these fringes we will see later about how the phase changes over time. So you saw this quite noisy from the level 0 SAR images. So take a close look at your exercise today. We're going to looking at Pitman Glacier, which is one of the largest glaciers in the north of the Greenland part. And think about you have the T1 and T2 in terms of the SAR region, in terms of SAR, the images. This is not multi-looking. I think this is it's a ground-based. The looks, not the single look. And if you do the interferometry, what we can get is this fringe. So normally, because you can like subtrate with one from the other one, and you can have this different stripe, or what we call fringe, and because the signal, the active one, is coming back and forth, so the displacement is about half of the wavelength one. And remember, so this is ice sheet, and this is kind of the ice shelf. So the ice shelf is kind of not directly linked to the ground. So that part we call ice shelf, and we will continue to have the actual data satellites such as the Earth's curvature or the topography data to remove or to flatten these images and completely get the movement because of this. Because I will give you a little bit example. So this is ice shelf part, and this is a grounded ice or ice sheet part. So because the tide can be flow and intrusion into this grounding line. So what we saw from the SAR images is normally like the constant movements of because the tide can make the ice shelf up and down. So normally it's quite constant and in a quite reasonable, like the phase and frequency. So in terms of grounding zone or grounding line, so we're normally using the SAR to detect, or interferometry SAR to detect this grounding zone. That is because on the one side, this what we call the ice and the ice shelf and the tide can have the flexure with each other. So the first important part is because it can move up and down, we need to have some like the estimation about where is the grounding, and it also detects the width of the grounding zone. So that part we can directly deduce from this interferometry SAR, especially when you continue to further subtract the interferometry SARs within 2 different the time or revisit the time. What we can use, like what we call is cone drop differences interferogram. So this is a SAR based the ground zones continue differentiate or to differences between different 2 interferometry the SARS images. So this is what we call the grounding zone. That is one side is more attached for what we call land lead, and the other side is more about the sea lead. So within this, the width or the width of this the grounding zone, we can literally know if the ice flow or the ice shelf is going to retreat or advanced. And that is about a little bit technique introduction about interferometry. And what you were exercise working on is how to detect this ice velocity from this quite simple algorithms. So because we don't want to visualize or to identify the fixtures by our own eyes or bare eyes, so what we normally do is using this kind of cross correlation matrix to find previously if you have the one picture in at T1 and you wanted to find where is it in terms of the time. So we wanted to construct this correlation matrix to build these correlations. So what we normally do is trying to identify the reference chip, and we also have the search chip in terms of or in a different time for the images, and then we do this correlation. And the maximum correlation, whatever it's maximum or the minimum, the maximum absolute correlation is what we detect the pictures. So here is one example for the Sentinel-1, and this is captured in February, which if you can detect, if we wanted to detect this picture here, and this is another snapshot from in November. So if we wanted to again find these pictures almost 8 months later, how do we find it? So we construct or make a little bit search in the wider regions and to build this cross correlation matrix. So we zoom into this little bit pictures, and for the wider kind of the searching chip, we construct this correlation map, and the largest one is the pictures that we detect before, and we continue to align it together. Literally can give us the signal about how much of the ice is being moved. So let's move on to the Jupiter part. Okay. So I've already have some the pip library. I'm not sure which version of Python you're using. So this is a 3.11. So here is a little bit like some library we are going to use in this the tutorial part, including the scikit and NumPy1. So first of all, it's very intuitively about this computing this the cross correlation part. So not just about the absolute value, but about the anomaly or a normalized value. And for the SAR images, what we normally using the library is the aim rate to read the TIFF file. And you can see this is just subtract subset of the images from just a small the size from the TIFF file. And for the window size one or the reference size one, which we normally narrate it down to whatever 30 or 40 as you wish. And then for the searching chip, you can make it into a larger one. And then I just give you an example about in which center or the coordinate system we're going to search. So this is going to extract into the reference chip or reference the window and the search window. I hope you can follow us right now. So this is exactly what I showed here in the slides about when we cut off or just select some substructures of the figures and how it look like. So the next step is going to, if you have this different size of the windows, and then you can, because we already have these functions to calculate this normalized cross correlations. And the next step is trying to find where is the maximum and to get index of the maximum. So here is about to find out where is the maximum and as well as this location. So this is like the cross correlation, the matrix one. And of course, you can select the max correlation from the start. That should be 0, not 1. And as you can see, the maximum correlation is about 0.7. So not always like 1.0. So might be lose some the signals or have some the noises, as we can understand. So again, when you have these two different locations from the start and afterwards, and in terms of the pixel size, which in our case about 10 meters, and you can literally like calculate how much of the in reality or geolocation the movement in terms of two different the time. So it's about 800 or almost about 900 meters. So that's it about how we are using the two different the times or acquisition times in terms of one, the Petermann glaciers, and how to detect how it's the velocity is look like. So, any questions from that part? Yes.
Is it then based on the fact that the shape remains the same? That's
You shift or?
the shape of the.
Yes, we are not about the shape, but what you are first of all find or to where is first of all find out where is your reference, like the size. So the reference must be very clear. Otherwise, you cannot find it in another way. So not just about the shape is fine, but maybe this point you can take as your reference or this part, but do not take the reference size too large or too broad, because otherwise your correlation, the matrix will be a little bit lower than you expected. So just maybe quite like spark or quite picky, the pictures will be very idealized. Here you can have a longer or different, because I bet in terms of a different, like the y-axis or the perpendicular axis of these images, you have very different velocity. Maybe the century of these glaciers is moving faster than the boundaries. You don't know. So this is also one of our like the concerns, because once we are dealing with these star images, it's always quite large to handle, because this is just two like subset of these TIFF images, which normally one TIFF about 1 gigabyte. So that's quite large. And just one snapshot, but I have to admit that they can provide us quite a high resolution, in our case, 10 meter. And shall we? Oh, super fast. Anyway, I need to catch up our pace. The second one is a little bit like in-depth application about, yes. Okay. Yeah, it's quite slow to respond to everything. So the second one is about continue using the Sentinel-1, but this time we're going to detect the aquifer. So give you a background about the aquifer. It's more like this is the aquifer that is height below the snow, but above the ice. So this aquifer is sometimes because of some percolation or melting from the top of snow, and like this is completely water, first of all. So some of the aquifers are like perennially, so they're always there, and maybe just refreezing and freezing, but the location is almost the same one. So this is the aquifer, and it's most important for us to detect where the ice sheet is fragile or instability. If we imagine if we have a larger, like the space of the aquifer, then it's this part of the ice might be unstable and easily to break up. So in the SAR, so we know the backscatter from the SAR, you have to know, but this backscatter is completely, first of all, depends on the surface or the dielectric surface of the, or dielectric properties of the surface, like in terms of the snow SAR, in terms of the ice, snow, and water one. So, you know, when we have the signals from the different, like the snow, water, and ice, what we normally have is once, you know, the backscatter is normally like to see how much of the signal coming back to the sensor. So once it's coming from the snow or ice to the water, you can see, you can literally feel it. The water can absorb more signal. So in this case, when we have the melt, we have less signal back to the sensor. That's why we have the less in backscatter or decreasing backscatter. On the other hand, if we assume that the winter season or refreezing season, that the water is becoming going to snow or ice cross again, then the backscatter will be going up. So in this case, we can literally just see where is the ice and where is the water, or where is the snow, where is the water. So in the aquifer, that's quite tricky because what we know the aquifer is high below the snow. So how to detect this aquifer? So the thing is, when we have the melting from the summer seasons, so of course we have decreasing in the scatter, but when it's going to refreezing, you know, the water have the higher or larger, what is called the heat capacity. So it will stop the snow becoming refreezing again. So in this case, if you have the aquifers, that's the going up of this backscatter will completely quite slow, because they have the heat or the heat release from these aquifers that stop the snow is going back to ice or going dry again. So in this case, we're trying. In this case, we use these differences, or in terms of the winter season or starting of the melting and end of the melting, to see how fast the backscatter can going up again, to see if we can respond so quickly, then we can pretty sure that there's no aquifer inside. If the slope or the what is called the response time is quite long, there might be the aquifer inside of it. I hope it's some principles can make you understand. So this is based on one reference, because they did a lot of the in-situ observations to align this backscatter from the SAR images. So as I said before, if you have the aquifer, so first of all, no aquifer, this backscatter can quickly going up. And if you have aquifer, that these waters within the aquifer will stop the snow refreezing again, then this backscatter will go slowly to going up. We use these differences, or at least some what we call the slope differences or rebundance, to define where is aquifer from the SAR. So if we look at this notebook again, sorry. A little bit slow. So if you open this Sentinel-1, this tutorial notebook will give you quite comprehensive about how we deal with this Sentinel-1 data together, because the previous SAR is just 2 images, and this one is more. In this quite abundant of the data, we are using a stack library to make them together. So again, would I normally open this is using the Raspberry? And then this is just give you example about, in this case, we're going to detect the Antarctic Peninsula, the masks, or this region's aquifer detection. So this is just completely first of all about the mask, because we wanted to focusing on this peninsula regions. So you can either to transfer from this CRS coordinate reference system to your EPSG. So it's a transformation from different coordinate system to another one, or from the geolocation to another one. And very useful, because I always have a trouble in detecting or select what is exactly, because in other cases, those coordinate system is quite important when you calculate literally the geolocation distance, like a kriging. So, okay. Here is, first of all, trying to collect all the data or read all the data, so you can find the data in the Sentinel-1 folder. If you, sorry, what?
Sorry, I was distracted.
No, it's, can you follow it or?
The Sentinel-1 data is really quick and it's too slow to download the Sentinel.
Oh,
And not most of the data, but not the Sentinel one. Yeah.
not Sentinel 1. Okay. Maybe you can try it later because I think Sentinel 2 also have a quite large 2 GB.
That was more manageable.
Okay.
I think.
But Sentinel 2 is because Sentinel 2 is more about classification and which require more computational capacity. But anyway, we can take our a notebook as an example, and you can download by yourself. By yourself later. And this one is going to, because each of the data will have both TIFF file and CSV file. So it's more about how we read the data together. I'm not sure if you manage to read data in one folder or just read data one by one.
Yeah.
If you have any experience in the read data together or just one by one.
And downloading or?
In read the data.
Reading.
Yes. Because I'm not sure how your preference in reading the data.
Mm.
So this will give you about how I use the data as a open it together and then stack them together. So, okay. And here we can find, because we have every year we have one TIFF file, and for each of the TIFF file we have different bands. So in here we can just stack them together. So what I normally do is using append and then making the NumPy array, then stack together, and this is all the bands of what we get. This is the row and column. And afterwards is about how we align, because yes.
Increase the font size. Just increase the font size. The font
Control plus.
What?
Make it.
Oh, sorry. It's a little bit slow to respond for. I cannot. Can you because normally it's quite.
I think if you maybe press the direction, the top left, it goes away. Yeah, above. If you press it, yeah.
Okay. Yes, thank you. So the second step is, next step is going to, because we have the CSV file, and the files when we are loading it is not in what we call chronologically, like from the last year or smaller year to the larger year. And the next step is we want to align this time and date together with this CSV file. So if we continue to add this data into the list, they'll be perfect. And I really love the Panda, series, the function, because it will automatically convert and sort all the data list together and give you the index as well. So as you can see, after the index sorted, you have what is called chronological. I know. So then we have all the stack the data together. So next step is trying to do a little bit more analysis about how we select the data. So this is just simple select and extract the data from maybe one point to another point. So here is already some of the data already being, the noises have been already moved by such as the speckle noises. So here we wanted to see it more clearly. So maybe we have this smooth data, maybe from, because this is from, I think it's from daily one. Maybe we can make this 3 weeks or monthly smoothing to continue remove some noises. If you have one pixel and you got the time series of that pixel, because right now you have everything from 3D. So this is quite simple one, because it just find your pixel, get the time series, smooth the data, pull the data. And to see how this, remember we have the aquifer. We wanted to see how this different changes. So literally we want to average the pixels in their individual time series, right? So this will give you a little, if we select 3 different the system or the pixels. That's why transformation the grid cell is quite important, because right now we can just type in your longitude and latitude without typing your index. So find, disclose it, the pixel, because what right now identify the geolocation is not exactly the center of the pixels. So here is trying to do a just quite simple one about linear. Find where is the close pixels, and here is give you the time series to plot it. So this is the geolocation of the 3 different sites and give you the time series, how they look like. This is just the quite nasty one. So we're going to improve a little bit. So here it's just 7 years. Yeah, 7 years data in the 3 pixel or 3 different locations. And the next step, we are going to just select the melting seasons because that's what we really care about. We don't need the whole season. So in this case, again, using the pandas, like to sort out, because right now we already have the minimal year from the 2017 to 2023, and we just wanted to select the first of the July until the next year or until the next year seasons. So we wanted to make it into a full what we call melting and the freezing season instead of from the 1st of January to the last of the December part. We want to reshape this time date again. And this is what we got to restock or substock this the time series into one freezing, another freezing melting season. So you saw this plot as our reference. So the reference told us to make the differences between the 1st of the November, the 1st of April until the 1st of the September, how the differences look like. Because as you can see, it's quite easily to detect when we wanted to subtract or to make the differences between this date and this date, and we can easily to make some assumption or threshold to detect if there is an aquifer inside of it. And this is I think the 3 site that we just selected one, and again the following will be just masking how it look like and detect together. So this is October's backscatter and March backscatter. And when we are going to subtract them together, this is how it look like. Just in the unit of dB. And maybe this one is going to have the aquifer that can be detected because we have the threshold. So this is all 7 years, 2017 until 2022. And then we're going to apply, according to these differences, going to further filter it by these aquifers by some threshold. In this case, we're going to select minus 9.4 as the threshold, but you can adapt it to your own to see how it look like, which we were going to do that again, going to later. So this is how, in very simple, to use the functions to see where is the aquifer detection. So here it is. And remember, that's just the threshold that we're going to detect. We have no idea if we change the threshold, how much of the area of the aquifers can be detected. But to be, let's put this in this way. So this threshold is not quite, physical, clear, because it's purely arbitrary. So we have no idea if when we change the threshold, how much of the area can be achieved. Otherwise, it'll be super disaster. So in this case, we do a little bit split to divide the threshold from a smaller value to the larger value to see how the transition or how the total area will look like in terms of the choices of the threshold. So that is normally remote sensing the people are worried and struggling with, because the threshold is most NDVI is mostly used. But how to select or how to, based on your the algorithm to detect the type of the surface is user dependent. So here is again the total years, that because we have 7 years that have been identified as the aquifers, and as you can see, I have no idea where the location is, but it's near the George, because this is the George ice shelf part. And this is lesson C, which is quite recently changes. And again, about the pixels that we're going to use That is, so here I just changed the threshold from -10 or yes, from -10 to -6 to see how it look like. So when you select the strict threshold, of course, you have quite narrow or small aquifers, but the strict threshold will give you some quite larger confidence in this aquifer detection. So I think this one have like differentiate this threshold into different -1 as a step to see the total, the pixels or the total areas that can be identified at the aquifer. Next one is amazing part because previously is about pure threshold based, and the next is about what are we going to use in the ice bridge. That's OIB. That is the airborne based one, and it will give you. Have you ever heard about ice bridge or no? Anyway, it's just take this as the airborne data and give you a little bit ground truth based the data. So as I said, this is a airborne data, so it's not quite nice and easy to see it. So read it into from this CSV file, and it will give you some latitude and longitude in terms of how much of the depth it can be detected. So this airborne data can provide as the validation in terms of our aquifer, like the detection. So first of all, you want to see where they are. So these are the airborne tracks. Of course, they are institute and point to point. So normally the next one is trying to a late interpolation to make this tracks data into the mapping one that one normally do here from 1D to 2D, which here you can either using kriging or either using just here I just using the linear. Where is it? Yes, the linear one. Or you can use the inverse distance, whatever. But every different because it depends on the what do we call heterogeneous will be look like, because once you have quite rough the surface, it will be super differences when you turn from the tracks to the 2-dimension data. So here give you about how we detected this depth from the track space into like the 2-dimension data. But normally it's a little risky to do that because every time the reviewer will ask you why you are using this method and what kind of the uncertainty you can have. So I would recommend kriging in this case. The next one is about to combine them together because we have the aquifer detection from the satellite and we have the ice bridge one. So it's about how to combine them together about how much of the aquifers that can be detected or how many years that the aquifers is normally occurred around here. And this is how the ice bridge is going to combine together. But here I just stop the coding, but because it's a lot of like the discussion within it in terms of how much of the trust, how much of we can trust in terms of from this airborne data. And I think the amazing part about this tutorial is trying to integrate it or trying to compare with the satellite with the modeling data, which in our case, we have the RECMO model, which is a regional climate model and completely from the atmosphere, the model coupled or have the slab ocean coupling. So here the model can give us about downscaling into 2 times 2 kilometers resolution, which first of all, this model performance is quite good. So we can maybe directly compare the model output with the satellite data. So in our case, we make an assumption about, because for the model, we cannot, because the model output is have the aquifer. They only have the melt flux. So here we wanted to align with how much of the melt flux is coming from the model and compare to the aquifer detection to make it align if they are most consistent with each other and in which region. So I think I have one comparison. Not here? Yes. So this is just one and the annual mean of how much of the melt flux coming from the model, and how much of the is it all from model one? Yes. Here. So this is align them together about when we are detecting the larger aquifer as well as the large heat flux and accumulation part. But it's a little bit risky to do that because, first of all, you need to have quite good performance of the model. Otherwise, you can use just like the remote sensing as a kind of your historical run and use the model output as your future scenario, how it can be changed for the future one. So that is about the overall about how we detect aquifers from the Sentinel-1. So next, again, I'm not sure I can. Do you want to see the ASCAT or the GRACE? ASCAT is again detecting the melting, and it's quite a quick one, but it's about how much of the melt can be detected from the backscatter. It's also from the backscatter, but in a different way. And the GRACE is what we saw. It's about the mass loss. So here is amazing tutorial give you the animation about the total. Where's animation? Yes, about the here I just show you the Greenland, but you can also adapt it to the Antarctic, which I can share some. We can see it in the slide later about how it's changing over time and how it's related to the sea level rise. So I can just show both of them, and you can select which tutorial you have interest. So the backscatter, yes. A little bit more moment. Yes. So the scalerometer is, first of all, it's especially designed to. Have you heard Ed Softlin from yesterday or the day before? He is yes. He is the one who in Netherlands who is the main contributor for the scalerometer, because the scalerometer is more about to again show the roughness of the surface. That is quite simple way, right? So normally, what the scalerometer is designed for the wind, because when they have the quite strong wind, the surface or the ocean of the surface will be quite rough and quite have a like wave, or the wave height is quite high. So when you have a quite smooth surface, then the backscatter will have some what we call Lamberni scattering. So you can have nothing from the scalerometer. So normally it's used for the surface, especially for the ocean surface wind retrieval. And in this case, of course, because you have two like this walls, it give you quite high, the wider the swath region. I think in total, yes, 100K. Oh, sorry, 1000K, which is an amazing one. But in terms of the SAR and backscatter from the scalerometer, which is quite different because the scalerometer is quite rough compared to or quite coarse resolution compared to the SAR. But again, the SAR is quite what we call the region dependent, because in different regions you have different mode. The scalerometer can give you the overall consistent one. And the scalerometer can give you, because it can detect the surface roughness. Of course, when you have the melting, of course, the backscatter will be quite lower. When you have the ice or ice crust, the backscatter will be higher. Again, simplified from the SARs. So we can use this backscatter or some information to detect where is melting from this the signals one. So in a simplified way, this is quite, I know it's quite quick and dirty, but this is a quite unique and quite straightforward way to compare the melting to compare the melting with this the mean or the winter time, the backscatter. Because what we expect, the melting is quite lower compared to the winter time. So how much of the lower, we maybe choose different threshold again. So again, threshold based one. So here we also want to do some analysis with the couple model. So this is also the document that we are going to use. And this is a quite amazing accumulative, like the melting days coming from the ASCAP. And starting, I think it's a accumulative one, just one example or accumulated days. But yes, you can see it's mainly, we can see it's, the melting is mostly occurred during the Lacency region and Georgia region. And if you take a look at the different accumulative melting days in the different years, which quite disparity or give you quite differences. So we are also working and mostly interested in the last day of melting, because the last day of melting gives us some hint about if the regions is extreme or experiments a lot of like melting or a lot of warming events. And will give us some the implication about maybe this when we have a lot of warming events, this region might be unstable in this stability. So, which again, just 3 years comparison in terms of the last day of the melting. Because when we detect the melting, and you have the whole, like the date of melting, and you can select the last day as the reference. So again, this is a little bit comparison with the climate model, which I think is quite, for me, it's surprised that sometimes they can match with each other in terms of the 2020, and both of them shows a quite large melting or the melting days or last day of the melting, but in some years they are not quite aligned with each other. So again, let's remember to, my understanding is trying to calibrate a little bit in terms of the climate model input, or at least trying to tune the climate model in terms of some parameterizations. So this is about the melting days from the ISCAT. And the last one is the one before last one is ice sheet mass balance from the Greece one. So do you know, how many of you know Greece and how to working? You too. So the Greece is have twins. So in general speaking, or because I'm not the expert in Greece, so the Greece is more like having two satellites together, and once come to the quite the mass regions, because for the Greece, they detect the distance between these two satellites. Once they pass through the quite the mass regions, because the gravitational and this this part of the mass can have the pulling forcing for these two different satellites. So I don't have the quite amazing slides show here, but one is going pass through, such as the Antarctic, then their distance might be changed. So according to the distance changing, we can approximately to estimate the total mass within the Antarctic or the Greenland. So for this data set, the data is quite rough, about 100 kilometers for the resolution. So this can give us a little bit about how much, like in general, will be lost, but not in a precisely way. So the Greece data, again, have to put the satellite and then transmitted these signals together and measure distance all the time. So in the Greece that we can literally, here is Antarctic, the ice, the mass from the Greece data, that is an anomaly one. As you can see, since 2002, it's continuously going down, but it's going stable until recently, which is also the one of the hot topic right now, to see why we see non-stopping the decreasing for these Antarctic mass balance again. And when we look at or zoom in the figures from the Greece data, this is the mass balance changes, and this is accelerated, or how much of the fast it can have the decreasing or increasing. If it is decreasing, and the decreasing is faster than before. If it is increasing, and then increasing also the faster. So quite imbalanced in terms of Antarctic. So if you also see, or you also can derive this GIF in your notebook, and to see how it looks like in different years. So this is for the Antarctic. And one thing we mentioned about, because once we melting all the ice, the sea level rise might be going up, right? But what the true? So if we take a close at the sea level rise contribution or anomaly, as you can see, of course, most of the regions have the sea level rise, but in this case, have a sea level decreasing. Why? Yes, good. Because this part have lost a lot of the ice. So previously, the ice can attract more the ocean or the water. When it's lost the like mass, they are gravitational. The forcing will be losing down. So first of all, you can see it quite clearly to see for the regional one, it's a sea level decreasing, but in general, it's sea level rise. So that is for the Antarctic, and we also see this phenomenon for the Greenland one. Again, the Greenland is overall in decreasing, and some regions has accelerated decreasing, but some regions are still decreasing in the same speed. And again, this is the plot from the Greenland, and when we take a look at how much of the sea level can be attributed to them, a little bit of decreasing for the sea level, but in general, it's the sea level rise. So yes, it's the first time when I show this to my students, they are all like, do not trust these results. So here, I think that is just quite quick overlook about this the melting from the ISCAT and mass balance from the Greece one. And before, that is more comparison. And it's all in the notebook if you wanted to take a look or at least to give a try. The last part about the classification. So it's completely based on machine learning, which I use quite simple one about UNet networking. And this is from, the data is from Sentinel-2 for optical sensor, because Sentinel-1 is not manageable for my computer anyway. So this one can be durable in your own laptop, even though. So this is quite, because when we're talking about the machine learning, we must have the train data, or at least trustable data for training. In this case, we are focusing on a smaller regions. It's called Hudson Bay. Because in Hudson Bay, the Canadian, the polar, their program have amazing the ice chart or ice mapping to see what type of sea ice it is from the quite fine resolution part. This is how their sea ice chart look like. This is all covered. The red part is all covered by the ice, but in a different, like the type. Because some ice are quite bright. Some ice quite what we call pancake ice. I don't have the picture, but pancake ice is literally like a pancake, but it's because of its the brine rejection from the ice is completely different, and with some of the turbulence from the upper ocean, so it's informed or it's formed into a quite circle round. I should have the pictures for you, but this will give you how we are carrying on this project. So first of all, this is based on Sentinel-2, the images, and from the Sentinel-2, we are going what? So the data flow is, first of all, we have this the train data that is literally captured by quite fine resolution, more Hudson Bay one, and we wanted to see how we train or how we detect the data from Sentinel-2. So as we can see, there were 7 in total for the surface classification, but these 7 categories are not even distributed, because I have here some of the categories are have a lot of example or samples, but some are have only little samples. So one of the machine learning techniques, or the tricky, is trying to slice, rotate, do whatever to do or subtract your samples and increase your samples to make it like overall or underfitting or overfitting or underfitting, to make this different categories like evenly distributed a little bit. So here is more like how we are aligning this Sentinel-2 with this the ice chart. So here is quite straightforward about the UNet. Here is just the one standard, the version of the UNet. First about compacting or kind of trying to turn the 3D to 2D data into 1D to lose some spatial, but to detect the fine or pictures from this one-dimension data, and to add more non-linearity or make them like mix up together with the redo activation, and then do the max pooling, which I'm not sure if you understand what is max pooling does, but it's actually make more deep learning about the pictures from the 1D, and then going to encoding again to using this is the contraction part, and then going to upscaling again from 1D to 2D to 3D. So here is a UNet, which you already have your code in your notebook one. And of course, the machine learning or the critical point is trying to find out what is the loss function, what is your the matrix. Because here we try different, the optimizer, loss function, and metric. They can be very disaster when you have a wrongly combined. Here is an example. It's a quite technique one, which I will give you just one example about. So here is just an epoch, because it quite some time for you to train for the data. So here is used about the sparse category, the loss function, which is about quantitatively the loss function. And we're using this, again, the sparse category accuracy for the metric, which is their loss function or loss value is quite pretty well in terms of the accuracy is quite good. But when you change it, this quantitatively loss function into a different one, which gives you disaster, the performance in the training. So you need to be very careful about this loss function and matrix one. So if you want to choose this mean square error, we should normally choose one. And then might be you need to change the matrix into your what we call jacket index. So it will give you quite reasonable the data or the result part. And I give you an example about how we see the different data, or how we see the prediction max look like in terms of the different pixels for the Sentinel-2. But of course, as I said, because the ice chart or the type of data have evenly or unevenly distributed, so in some of the images you need to make it bright or slice it or rotate it to add your sample. So again, because we have quite less samples in terms of the label 2, 3, 4, right? So this is the error or confusion matrix. So you can see those types are quite have a larger uncertainty. And type 7, again, have a quite pretty good job. So the next, I think in the coding, you are also need to put or increase your sampling in terms of label 3 or label 2 to at least reduce this confusion matrix. So I'm not sure it's about time, but it's almost the end of the tutorial part. And let's go to the tutorial notebook again. For the ASCAT one, I think I'm not sure how many of you download ASCAT data, but it's quite easy to implement here. The ASCAT is for you, I think it's just on the stack the ASCAT data and trying to identify the melting and the data of the melting and compare with the recommended data, which I've already uploaded in the dataset, and just make comparison about 3 years. But you're free to download your own data and to compare more the years. So that is the ASCAT one. And for the grids one, which you can find all the coding here. And this is for the Greenland, and you can easily switch to the Antarctic. And one of the interesting part is trying to make some correlation with the sea level, the changes. Here, the sea level changes, we're using this data set, which is a sea level anomaly. And it's not just updated until 2023, but it's updated until this year. So you can easily to download from this Copernicus Marine Services yourself if you're interested in it. So this one is I just downloaded last year, so it's until 2023. And here you have amazing about how sea level how the sea level surface level anomaly look like, and how it can be linked and make some correlations in the Greenland part. So this is just a sea level trend, but you can do the sea level trend with your because in Greenland we have different basins. You can make another correlation with the sea level trend or surface or sea level anomaly with this mass changes over time to see which part in the basin contribute which part of the sea level trend. So that is for the Greece one. Yes.
Go to the whole world, to do according to the climate scenario, the whole world is development, right?
And you trust it, you could do the whole world.
I don't know if going to this be more reliable to have one place that built and one the intertwines of different.
Do you see the sea level anomaly here?
Yeah.
It's literally like you cannot detecting whether if the melting coming from the Greenland have the contribution from the South Ocean. So I would firstly suggest you to take a local one, maybe a small slice of longitude or latitude. And what I saw from the sea level anomaly is completely like another story when you are for example, if you make some connection or correlation between the Gulf Stream and the Greenland melting. So yes, you'll definitely find some correlations, but how could you make some explanation to it? Because Gulf Stream has the sea level changes as well. You don't know it's under the climate change signal or the signal coming from the melt. So as I said, let's just give you some evidence, but how to link this evidence. So it's an open question. I don't have a quite right answer or direct answer. Maybe you can first try out your satellite data and test it in your climate model. And the last part, which I also give you, is about Sentinel-2, the mapping. It's give you quite. I think I have the differences before. So this is before I provided the labels look like, which is of course you have a type 2 and type 3 have quite lower sample, but if you do a little bit slice rotation of your data in here, the rotate images, or to augment those images. So this is the data you're gonna have. Still a little bit too little about label 2, which is not your idealized case, because normally you wanted to have your labels as much even as possible. But we still have some a little bit increasing type 3, 4, and 6, but not too much. So that's why it's pretty worse and pretty dirty in the type 2. But this is all the data you're gonna see it. But of course, you can see it quite a little bit naughty because some of the regions, if you are looking by your eyes, they cannot detect it in a good way, like here. There were some that opens within the eyes, but you cannot see it after your classification. So what else? Yeah, I'll give you a lot of examples about how the performance in the Sentinel-2 and the classification, which I think most of you have interest in classification for a type or for a surface one, because I'm not sure. And you can, one thing about this one is you can change your learning rate. And if you reduce the learning rate, it will take more time to train. And you can start with 0.05 to have your learning rate. Because right now I select 0.1 of the 0.01. So what else? And yes, I think that is almost kind of rough overview about the Cryosphere remote sensing. I mean, that is not like exhaustiveness. So there'll be a lot of uncertainty and a lot of data set that I show here. When you have interest in, you can continue to explore every different of the satellite